common source stage. So for common source stage, I want to spend a little time on the discussion. I didn't actually spend much time on talking about the common source stage or amplifying stage in terms of talking about its operating region, or typically is referred to as the output swing. So if you look at these two examples that we use, as I said, what does it mean by having an output swing? Typically, if one wish to examine the output swing of a circuit, which is, we look at this terminal, and what is typical, if one wants to investigate an output swing of an amplifying circuit, what typically is being done is that I'm going to do the whole survey. What I mean by this is that I'm going to give you whatever possible input level, and then look at its output level. So it's like the large signal transfer function. So you want to generate a transfer function to look at when is the operation region changes. So if I want to do this, this is like more like an inverter. So if you look at input and output, what happened is that, let's just assuming we're looking at the DC level, you simply do a large sweep. So it's like I'm surveying the whole stage, looking from any possible input level and looking at what is the corresponding output level in response to the change in input. So if you look at this circuit, what happened is that you would assume that there's different operating stages. There's basically 3 stages. One is that if Vin is smaller than threshold, if I'm looking at this simple common source stage. So if it's smaller than threshold, what happens is that the transistor is off, therefore your output is actually at VDD, right? So this is VL at VDD. And in this region, M1 is off. Therefore, there's no current. ID equals to 0, therefore output equals to VDD, right? M1 is off, therefore there's no current drop. So once it passes, once this rises to M1 turns on, what happens is that you assume that this voltage is actually very large. So anytime you have large drain to source voltage, meaning that it's supposed to operate in saturation, right? Because VDS is large. So if you're looking at a transistor, once it turns on, it actually starts here at VDD. So this is, if I'm plotting VDS, IDS, this is the point once it turns on. It would turn on and it would actually move to this direction, right? So this is actually not a good, I should do it this way. So once it turns on, it should start, if I'm drawing multiple curves, you're assuming that the point of operation, because this will be depend on Vin, as this is Vin equals to threshold, and Vin is slightly higher than threshold. So if Vin increases, it goes to that direction. So you're assuming that it will actually move from here to here to here to here. If you're looking at transistors, it's moving from high VDS to lower, but as Vin increases, it moves to the left. Right? This is actually VL, same as VL. So if devices is still in saturation, what happens is that you will actually see a fairly large drop. And this slope is minus GMRD. Remember, small signal model. Even though it might not be a straight line, because remember, GM actually increases with increasing current when Bin increases. So it's not necessarily a straight line. I'm just using a straight line to represent that this is the highest gain region. Okay? Once it starts, I'm probably dropping too fast. Let's see if my R&D is not too high. It will drop like this. So the slope is minus GMRD. So what happened is that once your input reaches a level where, so inputs start rising as we go. So what happened is that there's this boundary. So once my input reaches this level, for example, this particular line, it reaches this level, what happened is that you would then enter the transition between saturation and, so this is saturation, this is linear. Okay? So in this case, how does one determine the difference between saturation and there's a turning point where it would then saturate. I should say it would then enter linear region. So there's three. Let me first draw the two region is M2 is in sat. So we'll start with being in sat and we'll move into linear region. So this is the way your intersecting point goes as input increases. Therefore, lastly, if I continue to rise my input, what happens is that this voltage would then drop down to below. Therefore, this would then become into saturation. So lastly, I will enter M3 is, sorry, there's only one. Lastly, it will then in linear region. So what is the difference between the two? Remember, this is Vin is VGS. So when VGS becomes smaller than VDA, this is VDS. Just want to make, let me get another color. So how does one determine this turning point, X, Y? So how does one determine where it ends? This is my operating region. It entered, when does it enter saturation? This is when VGS becomes higher than, becomes higher than GD minus, I should say VTH. So let me rewrite it. So this is VDS. This is, your output is actually VDS. So at this particular VDS, which is X, at this particular turning point, this VDS will be equals to VGS prom minus VTH. So this will be one threshold lower than that. I'm not sure whether you. So this will be high. This will be one threshold lower than your output. Okay? So this rises to a level where this drop to where there's a difference between gate and drain is reach one threshold. Or I should say, you could actually say VGD gate is one. The difference between the two is one threshold. So X is one threshold higher than Y. Is that right? Should I? So if this is X point, this will be X minus VTH. If I'm knowing that my turning point is X, then I don't know whether it's confusing. Let me just write it down. So at this turning point, this will simply be VGS prom, or V in prom. I should say V in prom. At this particular input, the difference, I should say input and output, voltage between input and output exactly at VTH. That's where your turning point is. Okay? And this is typically referred to as, from here to here, this is my output. This is referred to as the output swing. Okay? And this is my, if I'm looking at the input range, this range in input, this is input operation range. Okay? Yes. 是. Oh, yeah, because my input increases. So if I'm looking at, 如果我看这个实际上就是我在画 ID versus VDS， 所以我 input 增加的时候，我不是 current 一直往上跑吗？ current 一直往上跑，所以我 current 当我 current 往上跑的时候，我一开始没有开的话，它在这里，就是 VDD， 这边是 output 是这个是 output 嘛 ，output 在 VDD 嘛，然后它会一直往左边跑，因为我的电流一直往上啊。那我电流往上的时候，我电流会我的电压会降低，电压降低是这个公式啊，就是 Vout equals to VDD minus IDRD. So as ID increases, what happens is that my Vout drops. So this is like the low line, but I didn't draw the low line. Remember, we have the low line analysis. If you want to actually plot, it actually goes like. I forgot to turn it off. Okay. So if you're using the low line, then you know that it will shift at this intersecting point. But we're not plotting that. Just to get you a sense as input increases. This is when input increases. Therefore, your current level increases. So your output actually moves in this direction. Output voltage moves in this direction. So just to show your balancing current and output, the relationship between the two. Okay? So as I said, you're actually, what happened is that your maximum, when we talk about having small signal characteristic, you're only looking at a small little point. Let's say if I want to have the maximum, I should say symmetrical swing, meaning that if I'm standing right at the middle of the stage, I can move to the right, to the left with the same amount. That's the most optimal point you want. If I'm standing right at this edge, then I will drop out very easily. So typically you want to stand in the middle so that you get maximum swing when you dance. You get maximum flexibility. So what limits your output swing is actually two things. One is this term, the Vout maximum. In this case, it's actually either Vout max is 0, Vout max is VDD. So you only have one side limited. This is only, so your Vout minimum actually depends on VD set or the overdrive of your circuit. So your minimum levels depending on how much your device, this device, has to be still remain operated in saturation. Make sure it's operated in saturation. Therefore, this has to be high enough than a VD set or an overdrive. VGS or VGS minus, this is VGS minus VT. Okay, it has to be higher than VGS minus VT in order for this to happen. So this will be your minimum level, which is VGS minus VT. Okay? Okay. So I forgot what I want to talk about. So let's look at if I have two transistors. This is only one transistor. So what if I have the common source stage with PMOS load? So for a PMOS load version, it will be slightly more complicated because I have two transistors. So this will be M1, M2, VDD, VP. Okay? So I can do the same exercise as to applying a input sweep and looking at the output terminal at the same time. I can do the same thing. And what happened is that it will look something more like this. I'm just going to give the results so you get a sense as to the main difference between the two. You can do the analysis on your own, but I'm just going to show you what the results are. So what happened is that still, you start with the input ramping to turn on the transistor. So there will be a transition point where threshold, VTH. Because I have NMOS and PMOS, so I'm adding the notation of having the NMOS turn on. So remember, once it turns on, before it turns on, what happened to this transistor? Before this transistor turned on, the current coming down, if you think about it, it's like a CMOS logic example. So what happened is that ID2 equals to ID1. Even though my, let's assume that I have a VSB, VSB equals to VDD, this is for PMOS, minus VB. I'm assuming that this is, I already set it so that it turns on. So I know that this transistor M2 is always on. I have to make sure that it's always on. Otherwise, it doesn't function. So you want to make sure that it's on. But then, at the beginning, what happened is that if there's no headroom, if I, let's say, when V in is smaller in region 1, so I know that I'm making sure that the overdrive for PMOS is making sure the transistor is on. So in region 1, V in is smaller than threshold, meaning that ID1 equals to 0. That is to say ID2 also equals to 0. So you might think that it's confusing. How does, I'm already turned on the transistor, but there's no current. How does that happen? Remember, what determined the current? One is this above threshold, making sure that you have inversion charge. You have holes forming the channel, but you still need what? To conduct the current. You need carrier and then what? Two things to make drift current. Carriers and what? Electric field, yes. So how do I make ID2 equals to 0? I make VSD equals to 0. So if you go back to the equation, the only way when, if you go back to linear region equation, let me write it down. If I'm writing down the equation of PMOS, it's VGS VSG minus VTHP, right? So VSD minus 1/2 VSD squared. If I'm writing down the equation for PMOS in linear region, let's say if it's in linear region, do I get it right? Supposedly to be right. Okay. So to make sure that 0, one is that this is 0, the other is that this is 0. So when VSD is 0, then the current will be 0. So this is when VSD equals to 0, ID is 0. Even though this one is non-zero, even though you have inversion charge, but there's no drift, there's no electric field, lateral electric field to pull it. So that is to say that VSD equals to 0. So in this point, we know VSD equals to 0, therefore your output level equals to VDD, right? So you're starting at VDD when this transistor is off. Okay? So once this starts to turn on, this level is still very high. Therefore, this transistor will remain in linear region because it start at 0. So it can only move to by creating, dropping this level, output level is supposed to be deviate from VDD, drop down from VDD to create some headroom for M2 to start entering linear region. So you then have a small little room where it goes like this. So this is region 1, region 2. So once again, for region 1, M1, M2, we consider it both off. One is by channel off, the other is by field off. In this case, M1 starts in region 2. I don't have room, so M1 is on, is in saturation. The reason why I know it's in saturation is because this level is high. The drain level is high. So I know M1 is in sat, but M2 is in linear. Okay? So this will then give you a small resistance, which will also create a gain, but it will not be the gain we use to assume output resistance, RO2. So this is not desirable operation region. We actually wanted is here. Is region 3, where it has the highest gain. So in region 3, we want M1, both transistors in SAT. If both transistors are in SAT, that's where it creates a high gain of GM1, RO1, and parallel out. This is where the high gain regions occurred. And then finally, M1 will then, when M1 pass VD set, then it will then enter region 4, where M1 in linear and M2 in SAT. But it's useless because it does not provide high enough transconductance. So in this case, we also want to look at, this whole thing is to explore the stage, remember? So we want to know that my output, what limits my output swing? So this would then determine my output swing. I have VL max. This is VL max. This is VL minimum. So what determines these two numbers? So my VL max will then be determined by VB plus a threshold of P. So it will be determined by this level. This level can be slightly higher by one threshold by this bias level. And my VL minimum will be VD set of M1. Okay? So you actually have, compared to that, you actually have two boundaries. There's a headroom on the right and a headroom on the left. So So this is typically referred to as the headroom, meaning that you need to give some margin for your head before you hit your head. So you need to keep some headroom on the bottom and some headroom on the front, on the top. Okay, so to make sure that there's a cushion between the head and the ceiling. And oh yeah, I want to mention, typically this is to refer to as your max. Of course, we know that for a circuit, your minimum voltage is typically 0, where whatever the circuit is connected to, and the maximum voltage is VDD. That's the ceiling, or the 0 and VDD are referred to as. Sometimes you can hear the word of 0. The maximum level, or the minimum and maximum supply voltage. Sometimes it's referred to as the rail, meaning that your circuit has 2 rails that bound it. So if you can actually reach the rail, so this is my high rail or top rail, this is my bottom rail, which is 0. So in this case, I could actually reach one of the rail. That's called rail to rail. If I have a rail to rail output, that's the best I want. I want to make sure that I can use the whole stage. That's rail to rail. So sometimes you will see a design claiming that it could reach rail to rail, meaning that it can maximize output range. In this case, of course, we have some margin. So you need to minus that headroom in order to get the operation region. This is the desirable operation region, which will provide you with the highest gain. Okay? So let's look at another variation. There's actually many different ways of doing biasing or loading. So let's look at a pretty special but not very commonly used. So we talk about the third common. Instead of having a PMOS load, I'm going to use an MOS. We call the diode connected. The reason why it's called diode connected is because this comes from bipolar junction transistor. Let's say if I have a bipolar junction transistor, looks something like this. If I connected the base and collector, I short the base and collector, what I see is actually a diode, right? I only have PN, so I can see it. It becomes similar to a diode. Behavior looks like a diode. That's why it's called diode connected load. But this is also be extended to MOSFET. So anytime if I have gate, even though it's not essentially a diode, sorry. So if the gate drain or short is also referred to, this is referred to as a diode connected structure. It's called diode connected when gate and drain is short. They're short together. Okay? So let's look at what happens if I have a MOS diode connected load. So what you do is actually simply follow small signal model to do some analysis, and there'll be very interesting results. So instead of having a PMOS drain, you will be looking into a MOS source when this happens. So this will then be my input as well. This will be my output. So coupling, V in, V out. So the circuit will look something like this. So to analyze this type of circuit, one needs to also construct a small signal model, right? So small signal equivalent circuit. So small signal equivalent circuit will look something like this. I will then have GM1 VGS. This is grounded VGS. Okay? You could ignore RO just to simplify the case. The main reason is because anytime you're looking into the source, that will actually give you low resistance. So this will be dominated by this very diode connected. If you look at a diode, it's a low resistance component. So this actually creates a very low resistance. So any RO would then be negligible. So let's first ignore. You can go back and add it back, but it would make very little difference. Okay? So if I'm looking at this is another V, I should say, this will then be connected. This is the drain that will be connected to another. The current will be flowing. I don't want to make any confusion. So this is the source. Therefore, your current is flowing in this direction. This is VGS, GM2, VGS2. And then my gate, let me just be precise otherwise. So let's label it. This is gate 1, source 1. So this is drain 1, source 1. Drain 1 and source 1 are connected together. And another is the gate. This is supposed to be drain 2. Is connected to gate 2 because it's shorted. And then the output terminal, bring to the gate 2, and source. This is grounded as VDD, so this is source 2. And I will have a VGS 2. Okay? So this is this part is M1. Sorry, it's supposed to be source. It is source 2. Sorry, I made a mistake here. This is the output is source 2. Okay? Yeah. So because I have diode connected structure, so if you look at this, if I'm looking into here, if I want to simulate what it looks like, this part will be the current. The current is GM VGS. And the voltage across is GM VGS. It's VGS2. So the effective resistance, if I'm looking up, Rx, it will be effectively should be precise, GM2. Because the current coming down and the voltage across is actually the same, inverse proportional to the current itself. Direct current control this voltage across. I should say the voltage across directly control the current. Therefore, it's a resistive element if I have it diode connected. remember, transconductance is when the third terminal control. But when this is connected together, so there's just the voltage across controlling this. So it looks like a resistance instead. So what happened is that you would then see something more like this. So the effective resistance, because of the negative sign, I should add a negative sign, so that it will look effectively equivalent to, and when redrawing the circuit, it will look more like this, GM1 VGS. And whatever I'm looking in, it will be effectively equivalent to 1 over GM2. Okay? And this is my output terminal. So then this will be VGS1, and this is Vin. So overall, I should be able to get a voltage gain, which by definition is VL over Vn, and it should be approximately GM1 times GM2 over 1. Okay? And if I already know that the current ID1 equals to ID2, because there's only one current branch. That is to say, if I want to write my GM, GM will be, if my IDs are constant, so that your GM equation will be let's write down the GM equation if your current is GM2 and we know that ID1 equals to ID2. So if I put this number up, this will be minus okay? So this is a very surprising, or I should say, wouldn't be surprising, but this will give you a gain which will be determined by transistor ratio. This is very, very useful if you want to have a linear gain. What I mean by this is that if you're looking at the left, this particular amplifier, if my current changes, meaning even though both of them, GM and RO, depends on current, therefore, this will not be a linear curve. I could only say that the slope depends on this, but the slope changes across the region. So that means that there will be a little distortion on my amplification. For example, the gain at this level may be smaller, that there will be higher gain at this level when the current is lower. Because we know that the gain is a square root independent, depending, typically, if this type of gain, the voltage gain is there's a bias dependency. Therefore, once my biasing point changes or my signal is large, meaning the current level changes, that will then lead to some nonlinear distortion of the signal. So if I want to have a linear amplification, you will see that this gain is independent. It's defined when the structure is being made. So it's independent Vn or VL. Or if you think about it, it's independent. If it's within the region, it's independent of IDQ. The reason why we say that this is not a linear gain is because it will change. GM and RO both depend on current. In this case, there's none of that. It only depends on device ratio. So once this has been made, and it will then provide a more linear amplification. So it will then have a more constant gain without but of course, this is typically limited to a very particular operation. So anytime you wanted to have a precise or precision in terms of gain. In this type of cases, you're not really sure the level of your gain. But in this case, it depends on whatever you draw. Therefore, you then be able to create something more precisely controlled. So it allows a constant voltage gain and better control. Even though it may not be very high, the voltage, the gain, the precision of the gain. I would like to, if you ever go into discussion, and we're actually going to skip that part, chapter 8. But what happened is that in typical operational amplifier type of design, what you do is that you make sure the gain is large enough, and you not really care exactly what it is. Just make sure that gain is larger than 1,000, for example. And then when you actually use the operational amplifier to do calculation, then the actual gain depends on the external circuit rather than the open, we call the open circuit gain. In real operation, you use it in a feedback loop, that sort of thing. So precision of gain is not necessarily very important when you're doing operational amplifier type of design. But if you want to have a precision gain within a small circuit, then this is the way to go. Okay, so there's various, of course this is not ideal. There's a lot of drawback of this circuit. Just to tell you, there's various ways of implementing common source or amplifying stage. It will then realize different, it will meet different purposes and realize different features, which you probably would will be desirable in certain applications. Okay?防疫规定啊，是不是规定开冷气还是要有一点窗户类似？你还是那边后面开一点点。我记得好像有规定什么，还是要有一点通风。但是这个最后面那边可能拉开，然后有点。 可以吗？ Okay, let's start today's discussion. So today's plan is to finish up on chapter 7, which is the single-stage amplifier using MOS transistors. So the first thing we're going to cover, we have already discussed a little bit on a common source architecture. It's very similar to a common emitter structure. The only difference, as we have already talked about, is that because you have a MOSFET which will have infinite input resistance, therefore it's actually easier to deal with the input resistant kind of problems. And then we're going to talk about a lot of different variations, as we did already address emitter degeneration. So we're going to talk about source degeneration. If you add resistors at the source end, what is the impact on the overall transistor behavior? And it's very similar to emitter degeneration. And we're going to talk about that a little bit. And then we're going to address also the impact of whether to include the early, I should say, channel length modulation effect, whether to assume that your output resistance of the transistor is infinite or is finite. If it's finite, of course, there's other implications as to it's more complicated when you look at it from the output terminal. So we're going to talk about that a little bit, the impact of having whether to consider R or not. So that's what we're going to address. And of course, we're going to talk about common gate structure as well. And last part is the source follower examples. So first, let's dive into the discussion of a common source. I should say use a different type of symbol. Let's start with the discussion of a common source amplifier with source degeneration, which is the structure is that I have a common source, meaning that inputs coming from gate, output is connected to the drain, and your source, rather than grounded common source, we have a resistors stacking on the source. So as we have already discussed previously, the main concept to give you an intuitive idea as to what happened is that because the voltage drop is rather than having all the voltage drop on the modulating, which is VGS, part of them has been divided to RS. Therefore, you're assuming that the sensitivity of the circuit become reduced, meaning that the controllability of the circuit. The controllability of a transistor is by transconductance, because by modulating voltage, you modulate the current. This will then lessen the effect. So it's like, as I said, it's a water-saving faucet. You add a sort of a rubber band around the faucet so that it will be less sensitive when you turn the knob. So that's the basic idea of having a source degeneration circuit. As I said, this is not very common in MOSFET because you will sometimes see examples, but it's not as used as common as that in bipolar. The main reason is because, as we already discussed before, MOSFET is not a very sensitive transistor itself. For bipolar transistor, because of the exponential nature, therefore, you will very often see this attenuation. It needs attenuation because it's sort of like an explosive device. The exponential factor will then lead to explosive current. Therefore, you probably need to add a attenuation. For MOSFET, you will see it mostly for different reasons, not necessarily to reduce the sensitivity, mostly for linearity. If you want to have a very linear amplification, then this type of structure will help in terms of linearity. But so that's the reason why we construct this type of circuit. So if you have this typical circuit, we want to look at the first principle is that we ignore the channel length modulation effect, meaning that you assume that you have an ideal current source when this is on, right? So this would then be my small signal model. This will be M1, right? So my input is at the gate terminal, output is at the drain terminal, and also the stack up of a resistor at a source terminal. So when we talk about input resistance, this is much easier because anytime if you're coming in from the gate, the resistance itself is infinite. And then we look at output resistance as we already discussed before because we're ignoring the effect of RO. Therefore, you're assuming this is ideal current source. Therefore, you're only seeing RD. That's another thing. You see only the effect of whatever is being externally added as your loading resistor. And lastly, if you want to analyze the overall gain, so the voltage gain, once we insert RS, the impact is we're going to assume that the gain will attenuate a little bit. And the way to do this is to find output voltage and in relation to input voltage. So output voltage is basically this current. The current is the same. So we know that the current is GM VGS going up. So the voltage at the output terminal is GM/VGS times RD. The minus sign is because of the direction of the current. And your input voltage is VGS plus another voltage. So this is VGS plus the voltage drop on RS, which is there's only one current coming down, right? So it's this voltage plus voltage across RS. That's what we get. So after eliminate, because both of them are in function of VGS, therefore you can get rid of VGS. And the final results will be its original RD attenuating by a factor of GMRS. So this look very familiar. It's whatever happened when you have resistors. Attenuation effect is amplifying by a factor of GMRS, or GMRE if you're using a bipolar counterpart. Okay? We could also look at what if you want to include RO? Let me make sure So the problem of including RO is that it will complicate things because you would then have another additional pathway between output and input. Therefore, you need to consider that. So you could, if RO is finite, we're still going to construct the same small signal model. The only difference is that this bridging between the gate and the drain and the source, there's a resistor in between. And then this is R out. So we're going to repeat the same exercise when RO is being included. GM VGS. Okay? So this will be my input terminal. This will then be my output terminal. So the way to address this is that we would then have something, there will be a current. So this is RD. So the way to do address this type of problem is then you establish a difference between this current. You need to know what is the amount of current that's passing through this RO. And this is being established by the voltage drop between VL and the voltage at this terminal VGS. So the way to do this, there's various ways of doing this. Let's just try that. So let's say you write down your input voltage. Let's deal with the first important thing is Rn is still infinite. There's no difference. So if you're looking at, if you want to address voltage gain, we start by looking at the output voltage. Or you can write the input voltage, depending on which way you want to approach. So input voltage will be this. The current, there was two branches of current. One is this current. The other is the current between the two. So your input voltage will be VGS plus RS times a current, which is VGS, a GM VGS, plus the current, which is VL, divided by should use, should I use the current? Let me think about which one is easier. Minus V in minus VGS. That's the current. That's the voltage at this particular point, which is in terms of input divided by this and divided by RO. Okay? So I'm writing down the current. The total current will be this, and plus additional current coming in from here. So you define it as a function of V out, right? And then we can also write down V out. Will be the same thing. V out will be the voltage, the current, I should say, the current, total amount of current, the same amount of current, plus V out minus V in minus VGS, RO, times RD. There's a minus sign. So that's total amount of current. This, I should say, I, whatever. Let me use a better, IS. Let's say this is IS. This is the same as IS. It's the same current because there's only one branch of current. This is the same as this. This is the same node. Okay? So you do some manipulation. Let me get the, because this result is more, not that straightforward. So let me just make sure that I got it right. Okay. So you simply insert that in, and then we can do some arrangements. And then lastly, you will get your output. I do not have this far. Okay. So the final results will be something like, again, you can do the manipulation and rearrange these parameters. The final output will be minus GM RO RS RO 1 plus GM R times RD. It looks slightly complicated, but it will converge to more simpler results. It should be the unitless number because GMRO is a unitless number and the ratio between resistors. So to look at whether it coincide when you assume RO is infinite. So based on this parameters, this equation, if my RO approaches infinite, this would then be GM RO RD. The bottom, you will see this part, RO will be larger. So you get rid of this, you get GM RD. 1 plus GM. Just to show that this equation should be consistent when it reaches boundaries. This is a more complete result. Okay?